Oh, perfect timing. Good morning, everyone. Let me turn on the screen. How's everybody? Awesome. Um, okay, so last night I finished scanning the last of the tests, so I had the scores should have been posted Sunday night. So this is in student view. If you'll go to grades, what you should see is for test one. Now mine is under the student test student, so it doesn't have anything uploaded. But you'll see under submissions, what I did is I made a submission, I submitted it for you, so I scanned your exam. That's what should be there. So you can review your score, questions, and everything else. I believe you can download it and print it out if you'd like. What I'd like you to think, many of you did very well on the first exam. Some didn't do as well as you would have liked, but look at it as sort of as a minimum grade. A few people have asked for a retest. They go, I can't do that. But then I thought, well, actually we will. So look at the final exam as a retest. It is your opportunity. If you did well, you could sort of not have to do so well there, which you probably will do just fine. But if you do better on the final exam, again, I will review that and I'll get you the benefit of that learning that took place. I don't like to give too much specifics because usually the coordinators will say you can do this, this, and this. But again, it's a holistic grading, so I do it on an individual basis. So just keep moving forward. If you have questions on the exam itself, I'd be happy to answer those questions either before class or we can make some arrangements over Zoom or whatever. But if you'll focus now on the newer material, because test 2 will only be specifically on the sections we've covered since then. We're not going to go back and pick up limits. Now, yes, we're going to have to probably be able to use the product rule, but there won't be a question specifically on the product rule, right? So focus on the newer content, keep up on track with that. We'll get some reviews. There is a review exam already available, but just kind of focus on this. Do well on the second test. I've seen a lot of students who didn't do so well on the second do well on didn't do so well on the first, do better on the second, and you can just keep on going because, as you're going to see, the skills for taking the derivative, we're actually pretty much done with that. Any techniques for taking the derivative, we're pretty much done. From here on out, it's going to be using the derivative. And then when we finish this stuff, it's going to be starting with the derivative and going back to the function. So it's kind of taking all those things and doing it backwards, and that's the rest of the class. So we'll pick up those things. Everyone still has that chance for an A in this class. Again, some it might be, if you're a little bit behind on some of the stuff, you haven't learned some, you might have more of a challenge, but everyone can still earn an A. A plus if you want. If you want access to the previous homework, I have closed it out, but on an individual basis, I'd be happy to extend it till the end of the class so you can access that for learning. I've told a few folks no because I don't want it to get in the way of your learning the stuff for test 2. I want you to do well on test 2 because with that you can pick up stuff from test 1. We have till the end of the course to work on that. But if you'd like to do it, I know sometimes the motivation is I want to get as many points as I can get, but you will also hopefully learn by doing it, and that's really what I hope the focus is anyway. Learning the content so you can go forward. Okay, so just a quick peek of where we're at. We're here today on 12.1. We're going to get into maximum, minimum, so the highest values and the lowest values. A lot of what we can do with algebra. We don't absolutely need calculus, but we'll sprinkle some calculus in at the beginning. We're going to look at more applications of what we're doing today. So today is primarily skills. We'll look at graphs and functions and determine how, the skill to find a maximum, the skill to find a minimum, which are really the same. And then we'll look at some applications. Then we go really only 2 more sections. We got a nice little fall break. And then we've got the second derivative, which is the derivative of the derivative. So you're just taking the derivative twice. It's really it's nothing new. It's just we're not done. Once we take the derivative, we've got to take the derivative again. And that gives us some more information about what we're doing. Okay. Then related rates, which actually takes us back to what we were doing in 11.5. So if you struggled a bit with that, related rates is a contextual type learning of implicit derivatives that hopefully will make that one even come more alive. We got a review. We got that second opportunity to do better and show how much you've learned, and then we'll move forward. Okay, so any questions, comments, concerns? You got your Powerball for that $1 million prize, $1 billion prize, millions. Yeah, millions like chump change now, right? I remember growing up, million was a lot of money. Now it gets you through a few years and you need more. So $1 billion. $1 billion. What would you do with $1 billion? It's always fun to think. Okay, so we're now into applications, chapter 12, 12.1, maxima and minima, sort of a Latin version of the maximum value and the minimum. So in a business setting, primarily what we're interested in, right? Maximizing profits. If we can get more profit out, we would like to do that. Minimizing cost. Okay, so those are things. However, there's also other things we can do. I've done some research on the nation of Bhutan because their national goal is not to increase gross domestic product, but to increase gross domestic happiness. So could we have a mathematical curve for what makes for happiness, and could we maximize that? That would be really cool, right? And I think that's when people are maximizing profit, they think that's going to maximize their happiness as well. The more you have, the more happy you're going to be. I find sometimes it's not the case. Sometimes when I had nothing, I was really happy because there was nothing to take care of either, right? I remember, an apartment in Albany, Oregon. We had no furniture, but we were happy. I got lots of furniture. That was a lot of housekeeping to do too, so a lot of dust gets on that stuff. Anyway, I think we're recording. Let's see if I started the recording. Yeah, good. Okay. So I'm going to skip over some of this stuff, but we'll go through a few of these. A lot of it is mathematical sort of definitions of what is a maximum. So I'm going to start off with a less than mathematical statement that if you're a hiker, when you get to the top of the mountain, you're at the summit, right? Here's our little smiley face. So this is a maximum. You've got the highest point, so you've got a good vantage. You look at the birds, birds are always trying to go to that maximum spot so they can see everything, right? The top of the tree, the top of the house, whatever. So that's what a maximum is. It's the highest point. It might not be the highest of everything, but it's the highest of where we are locally, right? You go to some places, or some buildings are taller than others, but if you're at the top of this building, you're at the maximum you can be for that building, right? So there's sort of two types of maximums. There's a local maximum for that area, and then there's an absolute that is the tallest of the tall. Okay, absolute. Oh, there it is right here, top of the universe. So I don't know what the top of the universe looks like, but it's really big. So you're at the highest peak of everything. So if we compare everything, we're there. It's not infinity, because infinity is a journey, right? You never really get there. So wherever you are, there's still further to go. So there's more higher. So infinity is not an absolute maximum. It's a journey to get there. But we'll see sometimes there's this absolute maximum. Sometimes there's not. Relative minimum, again, same concept, but the opposite way. So it's being at the bottom. So if we go down into a valley, we've got to come back up. There's only so far we can go. Do we have any scuba divers here? Go to the bottom of the ocean. Sometimes we try to go too far, right? And then you need some kind of a sub or something. But anyway, it's the bottom. It's the lowest point on our graph. Okay, so that's all the minimum is. And so you think of it, and these are all measured being low in terms of the y-coordinate, the output. Okay, we're going to see the x-coordinate gives us the location of where that's at. The y value gives us the value of the minimum. So this would be a lowest y-coordinate. And then same thing with absolute. It's really, really deep, or at least it's the deepest, it's the lowest of all the values. Okay, so the lowest of the low, bottom of the universe. And we're going to talk about things, sometimes we'll talk about a function and we'll have endpoints. We'll start, we'll have a start and stop place. Sometimes it won't, it'll be on an open interval, so we look at those, but we'll look at them. So again, highlighting when we look at the x value or the input into a function, that's going to give us the location of an extrema, location where we have a minimum or a maximum. Okay, doesn't tell us whether it's a minimum or maximum by itself, but it tells us a location that at this x value we have either a minimum or a maximum. It's the y value that will give us whether it's a minimum or a maximum by comparison with other points on that graph. Okay, so it's the y that actually gives us the value. So in language we would say something like I have a minimum of -5 at 2. 2 is the x value, -5 would be the y value. So all of these, what we're talking about is a particular point on that function, on that graph. The x is the location, the y is the value. Okay. So here's an example of a curve, and it's got all the types of minimums and maximums that we're going to talk about. One of the first things I like to point out is that without using calculus, we have to check the endpoints, because the endpoints themselves may be minimums or maximums. Okay. The other places where we get minimums and maximums are places like this, like this, like this, and yes, like this. And we're going to, as we go through these slides, we're going to see that each one of these is a little different, but basically these ones that are smooth curves, we could use calculus, and if we took the derivative, if we found that tangent line, what would be the derivative? What would be the value of the tangent line? The slope of the tangent line at those points, those 3 points. Slope of the tangent line is 0, right? It's a horizontal line, so it's a place of really no change. Again, we were decreasing getting there and then increasing, or vice versa, but that's a place where, so that's the one way we're going to use calculus. We won't talk too much about this point here. Whenever we have a sort of what we call a sharp point, a lot of times this is like the function absolute value of x gives us that, you can't take the derivative at this lowest point. And the reason you can't, someone asked about it yesterday, is because you could actually draw an infinite number of tangent lines through that point because it's a sharp point. So it's actually, the derivative is going to be undefined at that point. So that's again another special place. The homework might have one or two of these. We're not going to spend a lot of time on it because it's you really have to contrive the function to get the graph to look like that. But there's a few, okay? And then the endpoint. So we're going to check endpoints, and again, that's just taking a function, plugging in the x value, and figuring out what the y values are. And then you see what those are in relationship. The other thing we're going to do, we're going to take the derivative and find where the derivative is equal to 0. I think we've done some of those where it says find where the derivative is equal to 0. They were trying to get you ready for this section. Okay, wherever the derivative is 0, we're going to have either a maximum or a minimum. We don't know which. We have to look at more things. So again, these are just some more talk, and again, this one's emphasizing that the x coordinates, they give them some letters here, are the locations of minimum and maximum values. Okay, so these are our locations. We could talk about what's happening at coordinate b, right? The x value equals to b, and they highlight that at a, q, and s, a, q, and s, we have minimum values. Those are low values. Those are the bottom of the valley, if you want to think of it. And then at p, q, p, r, and b, we have things that, at least locally, are minimum or maximum values, right? They're the top. They're the higher than everything else around it. So again, this is the mathematical explanation. What is a relative extrema? What it's saying is basically it's the highest point compared to other points nearby. I like to just say it's in its neighborhood, it's the highest value. What's the neighborhood? Well, just a little bit. Could be a very small neighborhood or it could be a large neighborhood, but it's larger than all the ones relatively close by. Okay. Or it's smaller than all the values close by. Okay. So again, they point out the locations of those on that previous graph. And then, well, I think that's the next one. So here's what they're talking about sort of in a neighborhood. So we know at R there is a high point, a relative maximum. And then if you subtract some value h and add some value h, so you go to the left so much, you go to the right so much, whatever that is, it's larger than, the y value is larger than all the other y values. That's what we call a relative maximum. That's a mathematical definition of it. You could also just look at the graph and say, it looks like it's at the top. That's another way to think that's all the maximum is. Okay? But it's just, if we were to look at all the y values on that function, around R is going to have the largest y value. Okay. So again, this is sort of just saying that at R, the y value at R is going to be bigger than all the other y values that are nearby it, either to the left or the right. Okay, that's all that says. And again, we can do this by graphing it. We can see it. We can also, we'll go in and use the table feature. When you look at the y values, you'll see on above and below that y value, all the y values on either side would be smaller. Okay, so that's the biggest one. That's a relative maximum. If we had a relative minimum, it's basically the same thing, but the value at that point is going to be smaller than all the other y's. Right? Minimum. So costs are, it's the lowest of the cost of everything around it. Okay, that's all it is. And we're going to look at, in the homework they have you do it, probably, I think about 3 different ways. So we'll look at 3 examples directly from the homework on how to do this. It'll make more sense then. So yeah, we have relative extrema at P and R, and what we're going to see is that if we look for the absolute, that the absolute max is right here. And why is it the absolute? Well, because it's the largest y value. Okay, you just see it, right? It's the highest. That's what makes it the largest y value. Okay, and so we go through and yeah, what is an absolute maximum? Well, how many absolute maximums can you have? Just one, because if there was something that was more absolute or bigger than that, then that would be the absolute maximum. So you can only have one biggest. Now, the kind of hard thing to think about, could we have 2 points that have the maximum value? Sure. If you have twin towers and they're both the same height, that might be the maximum height for all the buildings in that city, but it occurs at 2 places, building A and building B, right? So we can do that, but it's still, we think, and we could have 3 or 4 different places where the absolute maximum value occurs, but there's only one absolute maximum value. That sort of makes intuitive truth, hopefully, but again, sometimes in math, it seems like math people just make things up and define things, but that's one thing that sort of does make sense. So we're only going to have one absolute maximum, and it's a comparison with everything, not just a small neighborhood, but with the whole function. So which one of the whole function, what is the highest y value? Absolute minimum, what is the smallest y value? Again, there can only be one of each. And again, it's instead of comparing to a small neighborhood, we're comparing to everything that's out there. So this one sees that at B we have the absolute max, and it ends up that at S we have the absolute minimum because it is the lowest of the low. Absolute minimum. Okay, for this, and again, we've got some endpoints, so this is all there is. We look at them, line them up. So again, it's going to be, the technique we're going to use is we're just going to look at a function, either the graph or the function or the table of values, one way or another, and we're just going to look for all these particular points. We're going to look at their y values. We're going to look for the biggest y value, that's the absolute max. We're going to look for the smallest y value, that's absolute min. And then the other ones we'll look at to determine whether they're a relative minimum or a relative maximum. And we're going to find that the graph is very helpful for doing that. So here's an example of a function, x squared plus 1. They don't have any endpoints here, so what's happening at these endpoints? Where are these going? We're not thinking of limits, but where do they point? Do they ever stop? No, they're going to go off to infinity. Both are going to positive infinity. So in this case, we'd say there's not going to be an absolute maximum. In fact, actually, there's not even going to be a relative maximum, right? Because those are always going up. There's no endpoint. But how about a minimum value? Well, we see right here, and so we'll introduce, what if we took the derivative of this function? X squared, its derivative is 2x to the first, right? 2 minus 1. Derivative of 1 is 0. So this is our derivative. If we set the derivative equal to 0, again, that's the derivative for the whole function. So at different places, it'll take on different values. So we want to find out where does it take on the value of 0. Because if it has a value of 0, remember this is a slope of a tangent line. That means we have a horizontal tangent line, which means that it's either a minimum or a maximum. Divide both sides by 2. 0 divided by 2 is 0. X equals 0. So we've got the x location. To find the y location, what we have to do is we go back to not the derivative function, but the original function. So again, this is where we start. We're going to use both the derivative function and the original function. The derivative function, we're looking for where it equals 0. That tells us the location, right? This is a location. And then to find the value, we plug it into the original equation, which is x squared plus 1. So we'll put 0 squared plus 1, and we find that f of 0 equals 1. And so this point, 0, 1, and how do we know that's a minimum? We really have to look at the graph. Or we'd look at table of values, or have to have some sort of knowledge. We'd have to sort of visualize it. But at this point, we just know that it is a minimum because of looking at the graph. In 2 more lectures, we look at the second derivative. There's a technique using the second derivative that will tell us whether that is a minimum or a maximum. So there are some additional tests we can use calculus for cases where maybe we can't graph it, can't look at it, but we will be able to do those, okay? But for right now, for this lesson, we're going to need to graph it, look at the graph. Oh, that's a minimum. Why is it a minimum? Because it's at the bottom. That's it, right? It's the bottom of the valley. Questions so far? Okay, so that's one way we can find it. We can use calculus. We could also not have used calculus. We could have just graphed it, used our graphing tools to find the minimum, and we're fine. So what I encourage you to do is use both. Go ahead and graph it. If it feels more comfortable to graph it first so you can see what's going on, and then use the calculus, do it that way, because you'll do more. You'll work through it. Maybe towards the end, because we'll give you 3 or 4 examples to work through. Try it the other way, where you maybe try to use the calculus first and then use the graph, but do the way that works best for you so you can kind of get through it. And then also remember, we do have an ebook which will give you some additional problems to work. I suggest working the odd ones because they give you the answers to those somewhere in the ebook. I think that you just have to click on it, but each book's a little different. But you could just do a quick look at some of the odd questions to get a little bit more practice. But we'll do some here. Okay, so this we already talked about, the terminology. So one way of saying this for this last one, that it has an absolute minimum value of 1. So whenever you see it talking about a value, we know it's talking about the y-coordinate. And when you're talking about location, so at 0 is a location, that's going to be the x value. Sometimes it's a little clearer if we could just list it as an ordered pair, and we know the first one's the x, the second one's the y. And sometimes we'll just say where it's at, that it's an absolute minimum without mentioning its value. So, but location is an x, value is a y. When we're talking minimum and maximum, we're comparing the y values, but we're also looking at the x values to say where that occurs. Okay. Here's an example of something with one maximum value that occurs at 2 places, right? So both of these are the highest values, but they're both the same. Whatever this number is, they're both the same. So there's two points that we can list as absolute maximums, but remember, there's really, as far as values, there's only one absolute maximum value. So now we're going to get into locating extrema. And we're going to introduce some vocabulary, and I struggled with this because this is the first book that uses this particular terminology that I'm aware of. In my upbringing, we just called these three interior ones, we call those critical points, and they refer to them also as critical points, and the reason we do that is if you use calculus without graphing, you find where the derivative is equal to 0 or where the derivative is undefined. Those are critical points. Those are places where either there's a minimum or a maximum, but you have to do a second test to figure out whether they're a minimum or a maximum. We'll pick those up later, but this class is based more on looking at the graph, so we'll actually be able to do that. But this text uses two additional words. So they use the word stationary point for where the derivative equals 0. So that's very specific. And think about stationary. If the derivative is 0, that means the rate of change is 0. That's stationary. It doesn't move. I just thought of that yesterday, and I've been teaching this for 2 years. I go, why do they call it stationary? It took me 2 years to catch up to that. Because the derivative is 0, it doesn't move. Okay. Singular points, because those are the ones that are very rare, and it's a place where the derivative is undefined. Okay, so we won't do so much with it because in business we don't get that too much. It's very rare occurrence, but we'll know that that's the other one, a singular point. It's just a point where we can't take the derivative or the derivative's undefined, and we'll look at a couple of those. And then the other places it can occur, notice they don't have any special names except, well, endpoints, the points that if we have a closed interval, we will have endpoints. Okay, and I remember going through calculus, oftentimes the endpoints are the ones I forget because I get so tied up in doing all the calculus. Of course, I was learning this without graphing calculators because they didn't have them back in the 80s. So I would forget about the endpoints. So I got in the practice of doing the endpoints first so that I wouldn't forget them. And we'll do that. And they're actually easier ones to do it because you don't use any calculus. So those are the types of minimum, maximum. Have stationary where the derivative equals 0. We have endpoints, and then occasionally we'll get these singular points where the derivative doesn't exist. And again, here's some explanation. Stationary extrema, that's wherever the derivative equals 0. Okay. But again, we might start off with just looking at the graph, and we can spot those without even doing any calculus. Okay. And then it's all this talk about singular extrema. We're going to kind of skip over that for now, and just that's the one that might pop up once in a while. When it does, we'll deal with it, but we can't. The derivative doesn't exist. And then endpoints, you'll see when I look at the examples, I'll typically start with the endpoints because, again, I don't want to forget them. Okay, and here's the graph we've been dealing with, and they've got everything labeled. Endpoint is the absolute maximum here. We have a relative minimum here at this endpoint. And if you read carefully, and this is the first time I did through the slides, one of the slides says you can't have a relative extreme minimum or maximum at an endpoint because you don't have one side, right? But then on this slide, they call the endpoint a relative minimum. So there's some inconsistency. Most books and on one of the exams, they made a deal of this, and one of the teachers says, some books say you can have a relative minimum, some say, so it's not well defined. So for that question, people got, it was a true-false. So if you said answer true, you got it right. If you answered false, you got it right. Because really, you can have, I would say there's a relative. Anyway, we're not going to worry too much about it, but it's certainly this left endpoint at A is not an absolute maximum, but for its area, it's certainly the lowest point there. That's what I would say. You go to the right, it's lower than all those points. So I would say relative minimum. And then we have all these other ones here. So let's go ahead and sort of move forward. Again, they give some definition how to do it. What we're going to do is we're just going to do it, and we'll follow these. Again, this is a lot of words. What does it mean? Well, you've got maybe 3 or 4 questions where they're going to give you in the homework that they will give you a graph. You're just going to look at this graph. What you're going to do is spot all the places that seem to be high points and low points. So if we go through this, right, there, for this area, there's a low point, there's a high point, there's a low point, there's a high point for that area. So it appears we've got 4 of them. And again, it's just a visual inspection. And then what we're going to do is list what those points are. And in the homework, when you start listing these, they're going to want you to go from left to right. So they want you to start with the smallest x value to the largest x value. So going by x values. If you don't, you may get some of them wrong, even though your answers are right, but they have to be in the order because that's how they have their checker set up. Okay, so I'll start that practice. I've got the point -9, and what's the y value? 0. Okay, so again, we've got a location is -9. We've got the value is 0. The next point I'm going to look at is -3, and the value that goes with that is 6. Next value I see has an x value of 3, a y value of -3, and then the last one, 9, 3. And then what you need to do is we need to classify these as minimums, maximums, relative minimums, relative maximums, absolutes, whatever they are. Okay, how many absolute maximums can we have? 1. Now, again, it could occur at 2 points, so there could be 2 of them, 2 points we call, but the value, the y value. So we look at these y values. I've got a 0, a 6, a -3, and a +3. Can you spot what is the biggest y value? Right here, right? So we're looking, 6 is the largest y value. That's got to be, and we can see it there, doesn't it even look like it? This is an absolute maximum. And again, from the graph we went down, we looked for all the places that are either minimums or maximums. We've listed them all, and then by the y values we can determine which ones are which. Do you see a smallest y value in that list of 4? -3, exactly. So the y value here, it's the smallest of all of them, so this has to be the absolute minimum. And what you'll see is on the homework they have like a drop-down list, and you're saying what kind of a critical point are each of these. And then let's go. So let's see, 9.3. Oh, that's over here. What kind? So these rest must be relative, right? Is that a relative max or a relative min? Max, because the ones next leading up to it are smaller. So this is we would identify as a relative minimum, even though it is an endpoint. That's what I would do. And then the other one at -9, it's 0. It's not the smallest of the small, but it is a relative minimum. Which of those points are stationary points? There's 2 of them. 2 of the points are stationary. And why are they stationary? Because the derivative, or the slope of the tangent line at those points would be equal to 0. Okay? So I don't know. Sometimes they'll ask you that, sometimes they won't. But stationary points. What are the other 2 points called? Endpoints. Good. So think through this. So these So given a graph, we can get it. Yes.
Wouldn't 9, 3 be a relative maximum?
9. Yes. Did I write? I thought I said it, but I obviously didn't write it. Thank you. 9.3, relative maximum. Thank you. Yeah, I'm ready for fall break already, so it's kind of like, although, just catch up on some work, I guess. Okay, all good? Okay, so again, you'll look at some of these. You'll get some examples, and this comes from the homework as well, but what'll change is obviously the red, I copied this, so the red numbers change. And then they'll give you maybe 2 or 3 of these where they give you an equation, they give you endpoints, and they're going to ask you to get the locations, find the exact location of all the relative and absolute extreme of the function. And again, they also give you some drop-down lists for you to identify whether it's a minimum or a maximum. Again, I encourage you, maybe if you're not feeling real strong at this yet, just go ahead and graph it and do it graphically. I'm going to just sort of attempt to do both, but I'll start with the analytical side of things, because that might be helpful. So where are the endpoints? -2, x equals -2, and x equals 2. So again, just for practice, because these are the things I sometimes forget, I'm going to find what was the function value at those endpoints. So -2 gives me, plug in -2 into the original function. And again, I do this because I don't have to do any calculus yet. And so it's a little bit clearer, and I don't get confused. Do I plug these values into the derivative, or do I plug them into the original function? And we always plug them into the original function. And we can figure it out. -2 to the third is -8. -8 times 4, -32. -12 times -2 is +24. And then I've got a +6. 24 plus 6 is 30. -32, so this answer should be -2. So when I plug -2 in, I get a value of -2. That's an endpoint, right? And again, we'll just leave that there. We've got to get the other ones, and we'll go from there. I'm going to put the other point, because again, I want to have them from smallest to largest. I'll put the right-hand endpoint down here, and I'll figure out what the derivative is to get the stationary points, and I'll put those in the middle. So I plug in +2. So here we go. 4, 2 cubed minus 12, 2 plus 6. And in this case, that's 8 times 4 is +32. -12 times +2 is -24 plus 6. That's 38 minus 24 is plus 14. So right away I can see, well, those are endpoints. Maybe -2 is some sort of a relative minimum, and maybe 14 is a relative maximum so far. But I got to get, I don't know what's happening in between, right? So we've got 2 endpoints, and somewhere, again, we're blindfolded right now, so we can't see the graph. We're going to look at it, and then it'll be clear. But how could I, if I'm starting out at this endpoint of -2, -2, I could either go up or I could go down. But how do I get either a minimum or a maximum? I got to go up, and then I got to come back down, right? That's the only way. If you keep going up forever, that goes to infinity. So what goes up has to come down. That's the only way you can get a maximum. The only way you can get a minimum is to go down and then come back up. So, and the only way to get those types of things is to have the derivative equal 0. Okay, so that's what we're going to do, is between these points we look for where is the derivative 0. So what do we have to start with? Well, we need that derivative. So we take the derivative of the function. 4x to the third. Remember, the 3 comes down. 3 times 4 is 12. Subtract 1 from the exponent, so it's 12x squared. Derivative of negative 12x is just going to be negative 12. X to the 0 power, which is 1. And then the derivative of 6 is 0, so that's all it is. What we do is we take that derivative, 12x squared minus 12. I wish I had a little bit more room here. I guess let me give myself a little bit of room here. We take 12x squared minus 12 equals 0. Now I did this with factoring in my other class, so you could watch this video if you want to see that. For you guys, I'm going to confuse a few people, so let me do it this way. I could add 12 to both sides, and then we get 12x squared equals 12. Divide both sides by 12. And that gives us x squared equals 1. And if we take the square root of both sides, remember when we do that we get a plus or minus. So what we're going to get is that when x equals plus 1 or x equals minus 1, that we've got a stationary point. We've got a place where the derivative is equal to 0. And what we could do is we could plug that back in up here, right? 1 squared is 1, times 12 is 12, 12 minus 12 is 0. Negative 1 squared is positive 1, times 12 is positive 12, minus 12 is 0. So you kind of just think through, oh yeah, those. If I plug either one of those in, I get 0. Now some of us might forget about that when we take the square root. I guess I should put that in there, right? That we get both the positive and negative values. That's where looking at the graph is going to help us. Oh wait, there's 2 stationary points. I forgot one of them. Oh yeah, if I use negative 1, it's there. So we can use our algebra skills here, but bottom line is what we need to do now is we need to plug in negative 1 and we need to plug in positive 1, because those are 2 places where there's either a minimum or maximum. We don't know yet. We're going to figure this out by getting the y value from the original function. Okay, so we've used the derivative function. We're sort of done with that derivative function now. So that's why I sort of do the second, maybe you want to cross it out, but we only use the derivative function to find the location of potential minimums or maximums. We throw it away and then we go back to the original function to get its y value, which is going to allow us to judge whether it's a minimum or a maximum. Okay, so negative 1 in here, again 4, negative 1 cubed minus 12 times negative 1 plus 6. Let's see if I can do this. Negative 1 cubed is still negative 1 times 4, that's negative 4. This is positive 12 plus 6, so that's 18 minus 4 is 14. Ooh, I see a 14 down here. It looks like maybe I'm going to get one of these where the maximum value of 14 occurs at 2 places. I mean, it's, unless this one does something for me, right? So, and again, I'm going to compare these y values to determine what's happening. But these, so far, these are the only 3 places. There's one more, this 4th place. This is the only place that we can have a minimum or a maximum. Cubed minus 12 times positive 1 plus 6. Let's see. This is going to, the first part gives us 4 minus 12. 4 minus 12 is negative 8 plus 6. We're at negative 2. Whoa, it looks like even the minimums are going to be the same, right? Because negative 2 is less than 14. And there's 2 places that negative 2 occurs. So it looks like we're going to have 2 absolute minimums. We have 1 absolute minimum value, but 2 places that occurs. We're going to have 1 absolute maximum value of 14, but 2 places that occurs. Okay. So I could label this, let's see if I can do this correctly. This would be an absolute max, and this would be an absolute max. This would be an absolute minimum, and this would be an absolute minimum. I guess M doesn't do it enough because there we go. Okay, so think through that. Now, let me go, while we're doing this at the same time, let's look at how this looks using the graphing calculator. So I don't think I had it open already. I should have done this. Let's see if it'll let me in without having me log in. Okay, it's coming. Oh, good. So what we do is we go to y equals. We're going to put the function in. And if I remember right, it was 4x to the third minus 12x. And this is a subtract 12x, not this negative. So part of when you're using the TI, you recognize there's two places that look like a negative. One is a subtraction, one is a negative. So you got to use the right one. We've got that. What I do when I do these is if you go to your window, remember our boundaries were from -2, and that's where I use the negative, to +2. So I'm just going to have the window be that size so I'm not distracted by anything else. Okay. In Desmos you can do this. Maybe we'll do that on one of the other ones. There's a way to just look at where you can actually cut the graph off at those points, and we'll show you that. I think those are okay. Yeah, Y max going to 20, because remember from our analysis we know that our maximum occurs at 14, the minimum occurs at -2. We should be able to see everything. So now when I go to the graph, this is what the graph looks like. Now you can see, isn't this much easier if you had no idea what was going on and you just graphed it? Would you be able to pick minimums and maximums graphically? Yeah, it's a lot easier because now we can see it. But we can also see that we did the analysis already. Here's -1. There's a, in fact, if I trace onto that, right? I can see that that looks like, yeah, 14. -1, it is 14. And then over here at +1, I trace down to that. Sometimes you can't get exactly there, but we did. We got -2. And then we could see our endpoints here. We can also go to the table. And again, we've got more information here, but we can see at when x is -2, which is one endpoint, we have that value of -2. A lot easier than plugging in the -2. So we don't always have to do that, but I want you to get the value that that's what's going on. Is we plugged in -2 for x, we calculated it. Calculator's doing the same thing, that just does it very quickly. We also see here that at -1 we have this maximum. It lets us know what's going on. At 0 we're down to 6, so we see that 14 is kind of a high point. At +1 we see our minimum of -2, and then at the value of 2, when x is 2, that location has a y value of 14. Okay, so same thing, we can look at the table of values. So that's where our technology has really helped us a lot. And even if you do this all analytically, I encourage you to look at the graph, because again, the graph gives you a greater picture and it brings it all together. And so if you can do it both ways, you will have the concepts down much more clearly. Again, it is one that you probably did this in your algebra class, and we can do this concept of minimums and maximums really all algebraically, simply by, because we have graphing calculators. calculus was used because 40 years ago we didn't have graphing calculators. 500 years ago we didn't have graphing calculators, and so they came up with this technique to kind of be able to make these graphs. Okay. So far so good? Okay. So that's what I like about there's this support. We can look at the graph, and from the graph we visually see what's the high point, what's the low point. That's really all we're doing. But then we've got some analytical tools that we can apply. Take a derivative. Okay, when it's equal to 0, that's that. Endpoints, all we have is algebra. Plug it in, arithmetic, right? And then it's just a matter, we're comparing the y values to figure out which one is absolute max, absolute min, and so forth. So let's look at this one, and maybe we'll go e to the x squared. That seems like a weird function, right? It's got, but we'll deal with it. How about this one? We'll start analytically. I'm not sorry. We'll start with the graph just to kind of see, because anyone know what that looks like? I know e to the x is supposed to be like a J shape, but there's got that x squared. I know x squared is like a parabola. I don't really know. Maybe it'd be nice to see what it looks like. I'm going to use Desmos with this one and show you how to get those endpoints in there where it will just drop off the graph. Someone reminded me this. So let's just pop into Desmos here. There's also a way to do it with the TI-84, but the syntax is much more complicated. So we'll just call this f of x equals e to the x squared. And actually you see it's kind of, it's got this parabola look to it, right? But I want the endpoints. Let's see, how do I do endpoints? I think if I put this curly brace and I put, what was the endpoint? -3 less than or equal to, less than or equal to x less than, less than or equal to +2. So those were the endpoints. Let's see if it worked. Oh, that's right. These values are so big, right? Let's see, if I put in -3, I take -3 and square it, it's 9e to the 9th power. Because I did this yesterday, I know that's up about 8,000. So just so we can kind of see that that actually happened, I'm going to, this maybe wasn't the best, I'm going to go with the y value upwards of, let's go to 10,000. And what you see is it cuts off here, right? So it's not looking beyond -3, and it also cut off at 2. Okay, but then I don't see much what's going on in this little part down here. So, but what I like about this is if I can zoom in and out and kind of just move it around. It doesn't, and maybe I go back. So I can see those endpoints, and we'll use those. Let's maybe just go to 20. And this to maybe, so we can see things. But we could kind of see a minimum here, right? And with Desmos, it's nice because if we click, it'll give it to us. So we see a minimum at 0, 1. And then we're going to see the only other place is those two endpoints. One is an absolute maximum just from the graph. The other one is a relative maximum. And then we have this one minimum here. Does that make sense so far? So we've looked at it. Again, we could also look at the table of values if we use the calculator. So maybe I'll bring this one in. Let's see, where are we? Good. We got, yeah. I think this is our last example anyway. So we're just fine. Let's do e raised to the x squared. And this time I'm just going to look at the table. Yeah, at -3, the y value is about 8,103. That's e to the ninth, or yeah, becomes e to the ninth power. I see when x is 0, right? Because from the graph I saw this, 1 is a minimum value. The values around it are higher. And then when x is 2, because that was the other endpoint, that gives us e to the fourth power. That's going to give us 54. Okay, so we can look those up and we'll just see. But what I want to do is come back here now and show you that a lot of times, oops, yeah, this is the last slide for today anyway. Oh, shoot. Give me this back. Okay. So, one thing they ask for is the exact location. Now, if we go to the calculator, remember that at -3 it was 8,100 and something. That's not actually exact, that's an approximate. What it's going to want is, so on this one we do the same thing. We check the endpoints. And we know that that's going to, from looking at the graph, we know that's going to give us our absolute maximum. So this is e to the -3 squared. -3 squared is 9. This is e to the ninth. This is an exact value because e is, this weird number that just keeps going on. If we turn it into a decimal, that's an approximate value. So if WebAssign had this as a question, that's the answer they want. They want just e to the ninth. That's an exact answer. And how can we label this one? Well, since we looked at the graph, we know that this is an absolute maximum. Okay, and we'll just go in order. We know. Well, actually, let me come back here. Let's play with this. We know that when x is 0, that was a minimum, and let's sort of verify that by taking the derivative. This is going to be a little bit of a challenge. E to the x squared. What is the derivative of e to the x squared? We know we need to use the chain rule. So what is the derivative? What's the outside derivative? It's just e to the x squared. Remember, anything with e in it, the outside derivative is a copy of it. We just rewrite it. But now we need to use the chain rule. We need to take the derivative. We need to multiply by the derivative of the exponent. What's 2x, right? The derivative of x squared is 2x. I'll put that in front because that's usually how they write it. That's its derivative. Okay. Remember, we want to find where this derivative equals 0. So we say 2x e to the x squared equals 0. And this is where we have to get a little tricky. We have two factors here, 2x, well actually 2 is a separate factor, but anyway, 2x and e to the x squared. These are two numbers. If one of them becomes 0, the whole thing becomes 0, right? Because 0 times anything is always 0. So this is where we can separate it. Either 2x equals 0 or e to the x squared equals 0. Well, 2x is only going to be equal to 0 divided by 2 when x equals 0. So there's one solution, and that's the one we have on the graph. But what about e to the x squared equals 0? Is that ever going to happen? Well, if you look, no, it's not. E to the x squared actually never does equal 0. And if you think of any function, e to any exponent, it can get close to 0. Remember, there's that horizontal asymptote at 0, but it's never going to be equal to 0. So this doesn't give us a solution. So we only had the one solution, x equals 0. We plug it into the original function, e to the 0 squared. 0 squared is still 0. E to the 0 is 1. Okay? And again, we did this graphically. We did it with the calculator. Now we're just kind of doing analytically. And then we look at plugging in 2, the other endpoint. We get e to the 2 squared, which gives us e to the 4, which is the exact value. Okay? So they want the, and what is this? Well, we saw from the graph that this is a relative max. The 1 here, that this is the absolute minimum. And you'll have a couple ones in the homework that have e to some power. Again, maybe start with a graph. Take a look at it. You'll find minimums and maximums. But then also go back and take some time to kind of do the derivatives. And what you're doing is you're picking up this ability to take the derivative. Okay. What we will do then is on Thursday, we'll look at 12.2, which is the same concepts, but it's going to be word problems, applications. So we'll have a context where we need to find a minimum maximum, but we're going to use these skills on Thursday. So we're going to keep building on this. And again, but no new ways to take a derivative or anything. We're done with that. We're just now using the derivative. Okay. So keep up the good progress. And again, let me know if you have any questions.